We know that feedback linearization is a very powerful technique which can be utilized to design controllers for nonlinear systems. And among the feedback linearization techniques, there are two important problems, that is full state linearization and input-output linearization. In the last lecture, we studied a systematic approach to obtain full state linearization of a nonlinear system, and we learned that if relative degree comes out to be equal to n, which is the dimensions of the state vector, then this state transformation will transform this system into this particular form, which is called normal form. And once we have this normal form, we can devise a control strategy to linearize this nonlinear system, that is to obtain an exact linearization of this particular nonlinear system. This is the case when a relative degree is equal to n. However, what if a relative degree comes out to be less than n? What will be the situation in that case? And in today's lecture, we shall talk about this particular situation. That is how to obtain an exact linearization of this nonlinear system if relative degree is less than n. So you remember that full state linearization problem is important when you are going to solve stabilization problem. And in stabilization problem, this output equation is less important, because in stabilization problem you only want that all the states, these converge to the equilibrium point. The output equation is less important. So what we can do is that we can define a dummy output such that for this newly defined output, the relative degree will be equal to n. So if we can find such an h for which the relative degree is equal to n, then rest of the procedure is simple. We can perform all those steps which we learned in the previous lecture to obtain full state linearization of a nonlinear system. Here is an example. Maybe we have talked about this example previously. We have a nonlinear system with this particular output. If we compute the relative degree, it comes out to be equal to 1. It is obvious that if we compute the first derivative of this thing, that will be equal to x2 dot, and in the equation of x2 dot, the control input u is appearing. That is, the relative degree is equal to 1, which is less than the dimensions of the system. However, for the same system, we can define some other output, dummy output, which is not the actual output of the system. And for this particular output, what we see is that the relative degree is equal to 2. In y dot, equation of y dot, the control input is not appearing, and in the equation for y double dot, the control input u is appearing, and the relative degree is equal to 2. Of course, not in the entire state space, but in a subset of the state space. So the procedure is now clear. If relative degree is less than n, we define a dummy output such that the relative degree is equal to n. Now there are two questions. Does there exist an h of x such that the relative degree corresponding to that h of x is equal to n? This is the first question. If it exists, then how to find that? In the previous example, we had done it by just by observation, but for more complex systems, it may not be possible to find such an output just by observation. So in today's lecture, we shall be answering these two questions. The answer of this first question is in this theorem. So this theorem states that the system described by the nonlinear equations written on the previous slides, that system is feedback linearizable if and only if there exists a domain d naught which is subset of domain D, such that this matrix has a rank equal to n for all x in the domain of interest, where this is adjoint of g of x along f of x. We have already learned how to compute it. Likewise, we compute up to n minus first adjoint of g of x along f of x and compute the rank of this matrix. If rank of this matrix comes out to be equal to n, it means that the system is full state linearizable. That is, there exists an h of x such that relative degree for that system is equal to n. An equivalent condition is over here, that is, the system will be feedback linearizable if and only if this distribution is involutive, distribution which is span of these vector fields. Again, we have talked about distribution. We have also learned what is an involutive distribution. So to check whether a system is feedback linearizable or not, that is, whether there exists an h of x corresponding to which relative degree is equal to n, you need to check one of these two conditions. And for example, here we have a nonlinear system, and we want to check whether this system is feedback linearizable or not. So we shall check the conditions which are enlisted in the theorem. We compute the adjoint of g along f of x, that is by definition equal to Lie bracket of f and g, which is given over here. We have already learned how to compute these Lie brackets and adjoint. So that can be easily computed. G of x is over here, its partial derivative with respect to x is 0. This is 0 matrix because this g is constant and its derivative with respect to x will be 0, and this is a 0 matrix. And then the partial derivative of f with respect to x is computed over here, multiplied by g. We have this expression, and which is equal to this thing. So we compute this matrix as described in the theorem on the previous slide. This matrix G, which is composed of this vector field G and this vector field, that is written over here. So what is the rank of this matrix? Rank of this matrix is equal to 2, not in the entire state space, but in a domain such that cosine of x2 is not equal to 2. So this matrix has rank equal to the dimensions of the system. Hence, this system is feedback linearizable. This distribution will be involutive, and the conditions of theorem on the previous slide are satisfied in this particular domain. Hence, the system is full state linearizable. Next question is how to find this particular h of x. So that is from the definition of relative degree. We want to find an h of x. We know such an h of x exists for this system. That is demonstrated in the previous slide because the conditions of theorems were satisfied. So such an h of x exists, and we want to find such an h of x which has a relative degree equal to 2. Relative degree equal to 2 means this thing, that is Lg h of x is equal to 0 and Lg Lf h of x is not equal to 0. This is from the definition of relative degree. So let's first see what is the implication of this first condition. For that purpose, we need to compute Lg h of x, and Lg h of x is equal to partial h over partial x into g of x, and we want it to be equal to 0. So you can easily compute this thing, partial h over partial x. The partial derivative of this function with respect to vector will be another vector given over here, and this is a g of x, which means that partial h over partial x2 should be equal to 0. So what is implication of this this statement? This statement is the same as this condition. So what is implication of this expression? Right. So this h of x is independent of x2. So this is one guideline which can be utilized to find an h of x. There is another guideline from this condition, and this condition means that this expression should not be equal to 0. And to compute this expression, first we need to compute Lie derivative of h of x along f of x. So that is given over here, and we already know that this h is independent of x2. Therefore partial h over partial x2 will be equal to 0, which means that this expression is equal to this thing, partial h over partial x1 multiplied by this thing, because this is 0. And then we need to compute this thing, and Lg Lf h of x is by definition equal to partial derivative of Lf h of x with respect to x1, its partial derivative with respect to x2 multiplied by g of x, and we want this to be not equal to 0, which means that this thing should not be equal to 0. This multiplied by 0 and this multiplied by 1, that is over here, this must not be equal to 0. So what is meaning of this thing? So this thing should be function of x2. So this thing is written over here, and this can be function of x2 only if this is not equal to 0. That is written over here, that is h of x should be some function of x1. So we have some guidelines for h of x. One guideline is over here, h of x is independent of x2. Another guideline, h of x is some function of x1. So we can take any function of x1 that will satisfy both of these conditions, and always simpler is better if it works. So we have selected this h of x to be equal to x1, and with this particular h of x, once we have selected h of x, then rest of the procedure is the same as we have done in the previous lecture. This state transformation will be a diffeomorphism. Now everyone can compute this Lf h of x, and that is written over here. And once we have this state transformation, we can write the system in new state variables z1 and z2, that is given over here, and by definition of this control input, this system will be linearized. However, remember that this is not the only choice of h of x. Any function of x1 will serve our purpose. For example, you could have chosen this function x1 plus x1 cube. This also satisfies both the conditions, and this is your homework. You have to take this h of x and obtain full state linearization of this nonlinear system. You will see that this complex h of x only complicates your calculations. Therefore, I always suggest you to choose simpler h of x. We demonstrate the same concept with one more example, and then we shall conclude today's lecture. We have this nonlinear system given by these state equations, where f of x is over here and g of x is given by this expression. Before we find h of x, we first see whether this system is full state linearizable or not, and therefore we have to check the conditions of the theorem. For that purpose, we need to compute this adjoint of g along f of x, its second adjoint and third adjoint. We already know the procedure. G of x is given over here, and this AD adjoint of g along f of x, that is by definition equal to this expression, and the partial derivative of g with respect to x, that is equal to 0, and the partial derivative of f with respect to x multiplied by g, so that is equal to the partial derivative of this term with respect to x1, with respect to x2, with respect to x3, and with respect to x4, and likewise other derivatives. So I have not written these terms over here, because whatever are these terms, those multiplied with zeros will become equal to 0. So I have only computed the last column of this matrix, which is the partial derivative of f with respect to x4. So partial derivative of this thing with respect to x4 is 0, partial derivative of this with respect to x4 is 0, partial derivative of this with respect to x4 is 1, and here again you do not have any x4, so this is 0. So this comes out to be equal to 0, 0 minus d 0. We have computed this thing. Next we would compute this expression. So this second adjoint by definition is given by this expression. This ADFG that has already been computed and written over here. Again it is some constant, its partial derivative with respect to x will be 0, and partial f over partial x ADFG. So over here I have computed the third column, rest I have not computed, because whatever is over here, that multiplied with 0, 0, and this 0 will be 0. So only this third column is computed, which is the derivative of f with respect to x3. So the derivative of this thing with respect to x3 is b, derivative of this term with respect to x3 is minus c, rest of the derivatives are 0. And then by simple multiplication you have this second adjoint, and next we compute this third adjoint, and which again by definition is given by this expression, and computations are simpler, and you can easily perform all those computations. And finally we need to check the rank of this matrix. We have this matrix, and what we can see is that if for example I expand it by this first column, and rather it is a lower triangle matrix, so its determinant will be simply equal to the product of elements at the diagonal, which is non-zero, which means determinant of this matrix is non-zero, and therefore this matrix is full rank. This matrix is full rank means this system is feedback linearizable, that is, an h of x exists for this system corresponding to which relative degree is equal to 4. So next step is find this. So this G has rank 4, the distribution is involutive, and the conditions of theorem are satisfied, and the system is full state linearizable. So we want to find an h of x, and we know such an h of x will exist for this particular system such that relative degree is equal to 4. Relative degree equal to 4 has this meaning: this is 0, this lead derivatives is 0, this is also 0, this is non-zero. So from these conditions we shall get some guidelines that will help us to select an h of x. So from the first condition we have lead derivative of h of x along g of x that we want to be equal to 0, so we compute it. Its partial derivative with respect to x multiplied by g, this is by definition. So partial h over partial x is given over here. Derivative of this function with respect to vector is this vector, and from here what do we get? D multiplied by partial h over partial x4, and we want it to be equal to 0. So what is implication of this statement? H should be independent of x4. Let's note down this guideline. H of x is independent of x4. This is from this requirement. Here is the second requirement, and to compute this thing, first we need to compute the Lie derivative of h along f of x. So LF h of x is given over here. It's partial derivative of h with respect to x multiplied by f of x. So I have written this to be equal to 0 because I know that h is independent of x4, and then multiplied by f of x, and here I get this thing after multiplication of this vector with this vector. And next I compute LG LF h of x, this expression, which you already know the procedure that is given over here. This this vector over here is vector g with which is written over here. So multiplication of these two vectors, that results into this expression. So what is implication of this statement? Right. LF h of x is independent of x4. LF h of x is independent of x4. So LF h of x, we have already computed it, that is written over here and is given by this expression. Here is no x4 over here, so here is x4, and for this thing to be independent of x4, this thing which is partial h over partial x3, that must be equal to 0. So partial h over partial x3 to be equal to 0 means that h of x is independent of x3. This is second guideline which comes from this statement. Next we have this statement, and let's compute it on over here. LF h of x, we have already computed it on the previous slide. The only difference is that we have also substituted partial h over partial x3 to be equal to 0 because this h is independent of x3. So we need second Lie derivative of h of x along f of x, that is given over here, and again after multiplication you have this expression. We have simply multiplied this vector with f of x is over here, and then we compute this condition, and after computations we have this expression. So what is implication of this statement? Second Lie derivative of h of x along f of x, that should be independent of x4. So LF square h of x is independent of x4, and we have already computed LF square h of x, which is given over here. So here is x4. For this this LF square h of x to be independent of x4, this term should be equal to 0. That is, partial derivative of LF h with respect to x3 should be equal to 0, which means that LF h of x, that should be independent of x3. This LF h of x is independent of x3. That is why its partial derivative with respect to x3 is equal to 0. And LF h of x we have already computed, that is given over here. For this expression to be independent of x3, partial h over partial x2 should be equal to 0. That means that h of x should be independent of x2 as well, because partial h over partial x2 must be equal to 0 for this thing to be independent of x3. So these are a few guidelines from here, and we also see the guideline from the last statement. And for that purpose we have written again the Lie derivative of second Lie derivative of h along f of x, that is given over here. We have again omitted the last term because we know that this LF square h of x is independent of x4. That is why we have not written the third term over here, which was basically x4 multiplied by some partial derivative. So thirdly derivative can also be computed, and after multiplication you have this expression. All of you can obtain these multiplications and perform these computations. And again this condition requires that this should not be equal to 0. What does that mean? This third Lie derivative of h that should be function of x4. LF cube h of x has already been computed, given over here. For this thing to be function of x4, this last term should not be equal to 0. Therefore LF square h partial derivative of this with respect to x3 should not be equal to 0. That is LF square h of x should be function of x3. For this thing to be function of x3, this partial derivative should not be equal to 0. That is LFH its partial derivative with respect to x2 should be non-zero, and this LFH is function of x2, and LFH we have computed it on a previous slide, and that is given over here, and we want it to be function of x2. For this to be function of x2, partial h over partial x1 should not be equal to 0, and that is h of x is function of x1. So we have some guidelines on the selection of h of x. It should be function of x1, it should not be function of x2, it should not be function of x3, it should not be function of x4. So let's again take this simple h of x, which is equal to x1. Once we have this h of x, rest of the procedure is very simple. You use this state transformation, and you can easily compute all these things. So after these computations you have this state transformation. Once you have this state transformation, you can represent the system in new state variables that is given over here, and it is the normal form, and by use of appropriate control law you can obtain its exact linearization, where this gamma of x and alpha of x these are given by these relations, and we have learned it how to compute all these things. So these two examples demonstrate that how to determine whether a system is feedback linearizable or not. If yes, then how to find an h of x which has relative degree equal to n. So here these examples give you some guidelines, but it is my personal observation that most of the time hit and trial also works, which is much more simpler in many cases. Here these guidelines, derivation of these guidelines, that is also tedious, and in many cases just hit and trial also works. For example, if I were given with this system, I would have tried it with the different h of x, for example h of x equal to x2, h of x equal to x3, and maybe finally h of x equal to x1, and would have reached at some conclusion. Of course that should be supported by some educated guess, and otherwise you can always follow these guidelines which are obtained from these conditions.